I'll be introducing myself. My name is Elad Shuster, and I'm a security data analyst at Akamai, the threat research team. Thank you for attending this presentation, and I'd like to thank OWASP for the opportunity to present the work we have done on this. Just before we start, how many of you are familiarized with HTTP2? Cool. And how much actually got to work with it? Maybe implement a client or a server or something like that? Cool. So this is the agenda for today. I'm going to be covering some usage statistics from Akamai's platform. I'll get into more details as what is the platform and how much traffic do we see. And this was the base for our research, for the data source for our research. Next, we'll do an overview of the protocol, get to know its key elements, and that would allow us to discuss the actual fingerprinting mechanism and the things we chose for the fingerprinting. Finally, we'll talk about some use cases, and hopefully we'll have time to touch about the attack landscape that we see in H2. A little bit about myself. Approximately 37 years old. As I've said, I work in the threat research team in Akamai and deeply enjoy my work. I love big data and single malt whiskeys. So if you have any, approach me later. And somewhere in my former professional life, I was a CPA actually, but ever since I've seen the light, so I'm okay now. This presentation is based on a white paper that we published a few months ago about the client fingerprinting, and some acknowledgements are due. It was led by Ori Segal, which is the leader of threat research, and Aaron Friedman, which at the time was a senior security researcher. So setting out to do the research, we needed data, and a lot of data. And I'd like to spend a few words on our data source. Sorry, this is the Akamai platform. For those of you who don't know Akamai, it's one of the leading CDN companies. And it hosts content for a lot of companies, huge companies across the world. And it has edge servers, about 220 edge servers worldwide, which are usually a hop away from like 90% of the internet users. And as a result, we get to see approximately 15 to 30% of all web traffic. That would include HTTP1 and HTTP2 traffic. Some statistics, usage statistics. We see about 1 billion requests of HTTP2 daily across 15,000 hosts, almost 16,000, sorry. And 27 million IPs using it. It's quite a lot of traffic. It's not a huge amount of traffic, but if we try to look at the ratios on the platform, it's approximately 10% of total traffic on the platform is HTTP2. So I've seen that the last stats that were published, I can't remember the source, were talking about 17% in the wide internet, but this is what we see. So from the platform and the data we see, we recorded the following data for the research. We've looked at 10 million HTTP2 connections, and I'll expand on what is an HTTP2 connection in a minute. And we've looked at over 40,000 unique user agents and hundreds of HTTP2 implementations. So a brief overview. For those of you who are not familiar with the protocol, it's based on a protocol called SPDY that was developed by Google. I think that it was around 2012. And it was published during 2015. And it actually were 2 RFCs published. The first one was dealing with the protocol itself. And the second one, the HPAC, was dealing with the compression mechanism, which I'll touch upon shortly. As opposed to the first version of HTTP, the second version is a binary protocol. That means that messages are no longer going in a text format. They are just a stream of bits. And it has a lot of implications. So HTTP1 had some challenges. And the first one is concurrency. The way to implement request concurrency in HTTP1 was by opening multiple TCP connections. And in each connection, we could send a request and get a response from the server. Anyone can think of why is it a problem? Okay. Sorry? Socket limit, especially overhead. TCP has a slow start mechanism for the control flow, and it's not really efficient to do it that way. There was a problem that if a huge response was clogging one of the connections, the connections would stay idle. It was not very efficient. The second issue was challenge was header compression, or the lack of header compression. As you've probably all of you seen HTTP1 requests or responses, it has headers. They are very verbose. They are repetitive. Sometimes the same value is going back and forth between the server and the client, and it's just not efficient and a perfect ground for compression. And lastly, the server is passive in HTTP1. And what I mean by that is that it cannot initiate sending of data without having the client ask it first. And maybe some of you are trying to think what's wrong with that. The client should ask the request and the server should serve. But if you think of it, when your browser requests an HTML page from a website, it would render it, and in 99% of the cases, it would generate requests for the static content, for the CSS, for the JavaScript file, for the images. So why wait? Why should the server wait for the browser to get the response, parse it, do the request? That's one of the challenges that was in HTTP1. And enter HTTP2. So for the concurrency part, we no longer have multiple TCP connections. We now have a request interleaved or multiplexed within a single TCP connection. As I've mentioned earlier, header compression was introduced in HPAC, which is the mechanism controlling the header compression in a different RFC. And the concept of server push was actually introduced and integrated into the RFC. By the way, clients can opt out. It's not a mandatory. I mean, a client can decide that he doesn't want the server to push anything to him. And so let's talk about the connection. We have a single TCP IP connection in which the data is going back and forth between the client and the server. Now, that connection is divided into streams. Streams are like logical sub-channels. We can think of them. Each one of them has a unique ID going from 0 and up. Where stream 0 is like the root stream. It's not particular to any request or responses. It relates to the control flow of other streams and the flow control of the connection itself. So if we look at the RFC, this is the definition of stream: an independent bidirectional sequence of frames exchanged between the server and the client. And now we're introduced into frames. Frame is the smallest unit of communication in the RFC. And there are 10 types of frames. They can be used for several purposes. There are frames which are which are designated to control the connection parameters. They are called settings frames. We have frames that deliver headers and data. We have priority frames, frames that control the stream management. And the last entity I'd like to introduce is a message. So just as in HTTP version 1, you could set a GET request, and it would have a headers, and you would get a response, which would have a header and probably maybe a body. The same could happen in HTTP 2. A message could be composed of one or more frames. In the example of a GET request, we would only have a headers frame, but if we get a response with a body content, we will have 2 frames in the response message. We will have a headers frame and a data frame. Okay. Oh, sorry. So just a quick recap. Those are the key elements. We've seen the frames, which are the smallest unit of communications. We've seen what streams are, which are flows of frames. Each of them is assigned a unique ID, and later on a priority. And we've seen what messages are, which are a logical grouping of frames into requests or responses. So these are the 10 types of frames that, that are defined in the RFC. As I've mentioned, we have a settings frame, which is controlling the connection settings, such as how much concurrent streams can be in a given moment at a connection, what should be the maximum frame size, and things like that. We have a headers and data frame, which are quite self-explanatory. We have a Windows Update frame, which is dealing with flow control. And we won't touch on all of them, but it's good to know there are 10 types of frames and different roles for each and every one of them. As I've mentioned, this is a binary protocol. So things are no longer messages are no longer exchanged as text messages. It would be a blobs of bits. And this is an example of how a frame structure is defined in the RFC. The first 24 bits control the length. Then we have a type. We have some flags, stream identifier. If you remember, each frame should be allocated with a stream to a certain stream, and of course the payload. So given that HTTP2 is binary protocol and it's almost 100% of the time transmitted over an encrypted channel, TLS, it could be, fairly hard to observe using just opening Wireshark or something like that. So we have some tools to assist with that. On the server side, I'm using a small weight server called NGHTTPD, which gives you a verbose log of all the messaging that goes back and forth in the connection. You can see each log line is representative of a frame. You get the type, you get the flags, you get the content. And on the client side, if you want to observe the messaging, you can either use verbose clients like NGHTTP or curl. There's one of the curl builds that supports HTTP2. But a nicer option would be to install that cute extension, Chrome extension, called HTTP2 and SPDY indicator. It would add that flash you see on the right to the URL bar, and whenever you are browsing to a site which is using HTTP2, it would flash blue. Otherwise, it would be gray. So first, it would allow you to see which site are you already interacting with in HTTP2, and if you click on that flashlight, on that flash sign, sorry, you would get a full verbose log of all the session, the messages, the frames for each of the sites you are browsing with HTTP. And as a side note, it's not only supports HTTP2, it does support QUIC and some other protocols. That's a really fun extension to use. So now that we've seen the great overview, let's start looking at actual log lines and see what messages are being transferred over the wire. So in the first line, we have a settings frame. Now remember, these lines were copied from a server log. So whenever you see a send, that means that the server is sending something to the client. And whenever you have received, that means that he's receiving a frame from the client. First of all, the server is sending a settings frame. And as I've mentioned earlier, settings frames are always transmitting assigned with a stream ID of 0. And within the frame itself, you can see a parameter that said the server is declaring that he wants no more than 100 concurrent streams at any given moment. Next, on the same stream, another message received from the client, another settings frame, a stream ID 0, and the client sends 3 parameters. So this is just just to give you some kind of an idea of how things are looking in the logs. This is another example from stream 15. This is the server received the headers frame from the client. Due to real estate space limitation, I did not include the headers, but this is a GET request. Next, the client sends a frame of type Windows Update on the same stream ID. The window size is usually set within the settings frame, the initial window size, and it can be changed for the entire connection or for a specific stream. And here it's incremented for the stream ID 15. And next, the server responds, sending a response with headers frame only. So let's talk about HTTP to conversation. Let's do a zoom out from a bit from the log lines. First of all, there's a negotiation. HTTP2 can be transmitted either over clear text or over an encrypted channel. And that's theoretical because I have never seen an HTTP2 implementation which is not using TLS. If it's going over a clear text, there's a header, an upgrade header that is used to indicate that the client would like to go and switch to HTTP2. And if it's based on an encrypted channel, within the TLS, there's an extension that is sent in the client hello. It's called the ALPN, the application level protocol negotiation, in which the client offers HTTP2, and the server can respond and say, OK, in the server hello, and then they complete the TLS handshake, and they start communicating over HTTP2. Next, we have the settings. The RFC states that upon connection, once a connection is established, both sides, endpoints of the connection, must send a settings frame. It could be an empty settings frame. Usually it isn't. But right after the connection is established, we get settings frame, which is going from the client to the server and from the server to the client. From a fingerprint point of view, this is perfect, because now we can try and observe and see some constant behavior, some default values, and that's really good. Once again, settings frame always go on stream 0. Next, after the settings have been exchanged, the client can send a request. In this example, I just brought the full request. You can see the headers. It's a GET request. You see it in the first header, that strange header I'll touch upon later. It's called a pseudo header. It's a GET request, and it's sent over stream ID 1. The RFC states that all the streams initiated by the client should be odd, where all the streams initiated by the server should be even. And the server responds with a message. And this time, the message is composed of 2 frames, a header frame and a data frame. Just as an HTTP response, one response could include headers and some body data in the body. OK. Well, hopefully by now you can get a better grasp of this chart. We have single TCP connections. We have streams, frames from different streams, multiplexed in that connection, and each endpoints know how to take those strings, those frames, and parse them and compose the messages. This is a small website. I encourage you to find it. You can just Google HTTP2 Akamai demo, and it shows the 2 images, the same image loaded with HTTP1 and then loaded with HTTP2. And the speed is really dependent on your connection. When I recorded that, I didn't have the best of connections. So you can see there's a lot of latency. And it was only 2 times faster. But you can try it out. And it could reach up to 4 times faster than HTTP1. And that's a nice test. So just Google Akamai demo, HTTP2 demo, and you should get to land in that page. So let's do a quick recap. We had version 1 of the protocol, which was text-based, and version 2, which is binary. They both can be transmitted either over clear text or an encrypted channel. The concurrency, where in version 1 used multiple TCP connections, now we have a single TCP connection on which requests are multiplexed. Just as a side note, H1 had a pipelining mechanism, which would potentially allow him to send more than 1 request, but I don't want to get into that. It's not in the scope. And 2 new features on the second protocol is the header compression via HPAC and the server push concept. And that's a quick, a nice illustration. I want you to take a look. I took it from the Nginx documentation site, showing a request in HTTP1 and H2, just to make it more clear what does a binary protocol mean. OK. So let's talk about passive client fingerprinting. As the name suggests, it's passive, and that means we do not inject anything into the client. We don't run any code in the client. We only observe attribute that the client is sending to us, and hopefully we will be able to expose some kind of a consistent, unique behavior. The general term for a passive client fingerprint is not only relating to the application layer. It could be done in any other layer, and it should be done as a combination of layers. The transport layer, looking at the TCP attributes, the session layer could be done with the TLS attributes, and application layer as well. Of course, that for HTTP 2, we are dealing with the application layer. One more important thing to make is we are not trying to fingerprint end users. We are fingerprinting software clients. We have no visibility into who's using those clients, and we are not trying to determine that. What we are trying to do is to deduce certain things about the client, like which OS type or version or he's running, what is the running software. Sometimes we can get the uptime. All of that by passively observing the attributes he sends. So for H2, we do that, and we observe the client's behavior while establishing a connection. And the first establishment of the connection is a very good point in time to do the fingerprinting, because a lot of the things which are hard-coded into the client, a lot of the default values just come up and are quite consistent. As far as you get from that, you get less and less accuracy. And we are looking for the attributes that he sends within the settings frame, like the flow control settings, the initial control settings, some priority settings. And the only thing which is a bit different is the last part, which I'll talk about, is the header order, the pseudo header order, because that is not sent immediately after a connection is established. We can only take that from the first request that the client sends. But we'll see that in a moment. So we spoke about the 10 types of frames. For the fingerprint that we are proposing, we deal with those 4, actually 3 in the headers. We look at the settings frame, at the Windows update, priority, and pseudo headers, and let's expand a little bit on describe each of them. So settings frame. As I've said, it conveys key and value parameters and their values that relate to the connection. It could be either flow control or the way that streams should behave, or things like enabling server push, yes or no. The default values of the parameters would vary between implementations, and that's perfect for fingerprinting. I'll show you an example in a minute. And once again, I've mentioned it, according to the RFC, all settings frames should be sent with string identifiers set to 0. So this is the full table of parameters defined in the RFC. There are 6 of them. And what I'd like you to note is you can just, presume they're pretty self-explanatory. We won't go over each and every one of them. But please note that each parameter has a unique ID assigned to him from 1 to 6. And this is an example, Firefox version 55 running on Mac OS X, El Capitan. Upon initiating a connection, would always send this setting frame with those 3 parameters, with those exact values. And of course, stream ID 0. If we look at a Safari on the same operating system, we now see different parameters and different value. It's now opting out of the push mechanism and setting the maximum concurrent strings to 100. By the way, the settings which are sent in the settings frame are mandatory. Each endpoint should respect that. It's not a suggestion. And I brought 2 more examples. One is from Edge browser over Windows 10, and the last one is from my Pixel XL. And if we put those in a table, and we did put them in a table for like 40,000 user agents, you can start seeing the differences. And once again, from fingerprinting point of view, that's perfect. So let's forge the fingerprint. So what we take for the first part, for the setting part, we take each pair and we just concatenate them together. The stream, the identifier of the parameter and the parameter value. Another example from Firefox, once again. You take 1 and the value, 4 and the value, 5 and the value. Next, we go to the Windows update. Now, a Windows update frame, as I've said, is a flow control frame dealing with flow control. And it increments the initial Windows size, which can be either set for the connection in the settings frame or for a certain stream. Some of these are default. RFC sets defaults for all of these, for the Windows sizes, either for a connection or for a stream. And along the life of the connection, any site can send a Windows update frame and just increment the size of the windows. What is interesting is that sometimes, upon initiating a connection, a client would not only send a settings frame, as he must do by the RFC, he would send right after it an update frame, Windows update frame, sorry. So this is an example from Chrome 60 on Android. In addition to the settings frame, which we just saw, we would have the Windows frame, Window update frame, and we collect that value as well. This is fingerprintable. By the way, if a frame is not sent, for any of the components, we just use 0 instead. That's a proposed fingerprint. You can do whatever is fitting for you. The third element is a priority frame. And that's really interesting because the RFC allows to create dependencies between different streams. If you look at the chart, you can see the asterisk stream. That's stream 0, the root stream. And then we have stream D, which is the parent stream. And stream C and E is dependent on the parent stream. And from stream C, we have A and B, which are dependent on them. So a priority frame would set these dependencies. For each stream, it would define on which stream he is dependent on, and it would give him some weights in terms of priorities. What are priorities? Essentially, it allows endpoints to express their preferences about allocating resources if the server has a limited capacity of sending. That means if you don't have enough resource to send everything in all the streams, please send everything to stream D. Next, send them to stream C and E, and divide the resources equally. You have weights over there. You see the 8 and 8. They are equally divided. When you're done with that, send data responses to A and B. And we have 4 and 12 as the weights. That means that 1/4 should be allocated to stream B, and 3/4 should be allocated to stream A. But there are no guarantees. The RFC does not mandate the server to respect that. It's only a suggestion in terms of what the endpoint would prefer that the server would do in case he has some kind of a sending capacity limit. But for our purposes, we found that to be very interesting that some client, in addition to sending a setting frame and a Windows update frame, would always send priority frames as well, would always set up that tree. And we collect that. We collect the data, we collect the weight and the stream dependency and the exclusivity bit. This is an example from Firefox. I did not include the former settings and update and the Windows update frame. You already saw them. But you can see that Firefox, upon initiating a connection, would create that tree structure, where it would create three main streams, numbered 3, 5, and 7. Remember, streams which are initiated by the client are always odd. And look at the weights. We have for stream number 3, the weight is 201, and that would be a high priority stream. And we have stream number 5 with weight of 101, and so on and so forth. And the question is, whether is that consistent? First of all, not all clients do it. There are certain clients implementations that do it. And we actually looked at the source code for Firefox, and I didn't bring the whole code, but those are the comments. You can see this is hard-coded. This is what Firefox would do every time it connects as an HTTP2 connection. So let's do a quick recap. We have 3 components up until now. You can see an example for a Chrome browser on Mac OS X. It's an El Capitan. We have the settings, we have the Windows update, and we have the priority. In this case, it was not sent, so we just plant a 0. This is the fingerprint of OKHTTP, a very commonly used library in Androids and other platforms. We can observe a different fingerprint for curl, which both don't send any priority frames. And this is another very widely used client called NGHTTP. And this one does not send a Windows update frame, but it does send priority frames. So we are starting to see some nice varieties. Well, that was nice, but still we did not have enough entropy. We could distinguish some versions and some OSs of browsers, but we had a lot of groups where a single fingerprint would include several browsers or several versions. So we tried to add one more component that would allow us to do some more distinguishing between the fingerprints. And that is the pseudo headers. As opposed to the other components, pseudo headers are not sent upon establishing a connection. Pseudo headers are sent when a headers frame is going from the client to the server, essentially on the first request from the client to the server. And these are not your classic HTTP headers. The RFC defines a closed set of headers. You have 4 for the request pseudo headers and 1 for the status pseudo headers. You cannot add to these, you cannot change them. The RFC explicitly states that any request with pseudo headers which are not defined within this closed set would be considered as invalid, so it would be dropped. And the thing is with pseudo headers, some of them collect some of the data that we were used to see in the start line of HTTP version 1, like the method and the resource, here it's called the path. Next we have the authority, which is the host, which we are used to seeing as a host, and the scheme, which is HTTPS or HTTP. After that, we get the usual headers, user HTTP headers, user agent, and accept. There are only 4 pseudo headers. And what is interesting about those pseudo headers, that they are sent in a specific order, and the order varies between different implementations. You can see that it's not the same with Firefox or Safari or curl or whatever, Go HTTP client. And that's another thing that we can add to the fingerprint that would give us more uniqueness and would allow us to distinguish between more and more clients. Again, this is an example from Chrome's source code showing that the headers is set by a certain order. It's hard-coded and not randomly chosen. So we have the final fingerprint. This is an example. We've discussed all of the elements, the settings, the Windows update, the priority, and the pseudo headers. And this is where we actually stopped. And that gave us quite a good results. Let's talk about the use cases. Fingerprinting can be used either for positive security or negative security if you want. You can actually look at the assertions a client is making in the user agent and try to see if you can expose browser impersonators or if you can detect certain automated tools which try to show themselves other tools or verify that they are who they claim they are. And one more cool application is that if you see an IP address from which a large amount of distinct fingerprints is originating from, you can then deduce that it's some kind of a shared IP. It could be either an anonymous proxy or a VPN or a corporate gateway or something like that. So that's one more thing. And the side note here is very important because using just the application layer for fingerprinting is not enough. Always try to combine as much layers as you can. It would add to the entropy. It would give you a greater distinction. It would give you, I don't know, looking at the TCP layer and looking if the OS matches the the OS you've seen in the application layer, and that's a really important thing to do. So, attack landscape. Currently, this is the attack landscape for HTTP2. And the reason is that most of the de facto standard tools of the trade don't support HTTP2. You have your list, and it's really long. The Burp, Zap, SQL Map, Hydra, Sentry, if you're into account checking. And I strolled around the exhibition area and asked some vendors to see if they are supporting like White Hat Security or NetSparker, and most of them still, it's just a matter of time, don't support. And there are some reasons for that, because there's no real incentive currently. Most of the web servers that operate with HTTP2 also have a fallback to HTTP1, so they can be compatible for as much users as they can. And HTTP2 libraries are not really common. There are some for some programming languages, but they are not really common and heavily used or heavily scrutinized. So the cost just exceeds the gain. And we don't see a lot of attacks over H2. I mean, I thought about bringing some statistics, but it's like a trinkle compared to HTTP1. It's nothing. And there was several server implementation weaknesses that were found during 2016. Those are not protocol flaws. They found some weaknesses in the way that several server implementations deal with header compression, or the way that stream management was implemented in those servers. So not a lot of exploitation going on over there as well. So I hope you got the key takeaways. I hope you got some basic understanding from this lecture of how the protocol works and its key element and the key differences between the HTTP1 and version 2 of the protocol. We've gone over the fingerprinting mechanism, the elements we chose. Other elements, such as the way acknowledgements are sent and things like that, are not consistent enough to add them into the fingerprint. And we've done an overview of the attack landscape, or actually lack of attacks currently. But it's just a matter of time. Things are going that direction. HTTP2 is getting some more and more attention. And hopefully this has been informative for most of you. Questions? Cool. Thank you very much.